today's problem is inverting a binary tree. So given the root of a binary tree, and sorry about my dog if you can hear it, we're going to invert the tree and return the root again. So for example, for this this tree, and I'm going to have trouble talking because I have to ignore barking noises, but just full disclosure. But yeah, so starting out at this top node, we're going to flip the 7 and the 2 here. And then for every other node, we're going to do the same. So once we go down here, we're going to flip the 7's children as well. So this 6 used to be on the left, and now it's on the right. And the 9 used to be on the right, and now it's on the left. So essentially flipping everything in the tree. And since this problem is a little bit, I'm not sure which ones lend themselves better to having TypeScript, but I feel like this one's definitely one of the ones where it's helpful. So I'm going to do it in here. Don't really have a rhyme or reason, but when I was practicing this problem beforehand, I ran into a lot of issues and I wanted to see what the errors actually were instead of just having this red line that I can't see what it means. But yeah, does everybody understand the problem statement? Okay, so just in case you aren't familiar with a binary tree, it just means there's 2 possible branches for each parent node. So we have this tree node class, which has a value. In this case, it does not matter at all. We don't ever need to use the value. We care about the references to each, I believe. Doesn't really say, but I would assume we care about the references and not the value of the nodes. But each tree node has a left and right property, which can either be tree nodes or null if there is no node. And then each of those tree nodes has a value left and right, etc. So looking down here for our constraints, we can either have 0 or we can have 0 to 100 nodes. And the example 3 does tell us this. So I think, and these node values don't matter at all. They're just there for whatever reason. So let's start with that. The easiest test case I can think of is just, what do we do when there is no nodes at all? You just return no nodes. And just since LeetCode might be doing this in a little bit of a different syntax than you may have seen, this is each row from left to right. So starting here, we have 4, which is the top, and then its children are 2 and 7, and then 1, 3, 6, 9, so left to right once you get through each of these. So we already have that test case in LeetCode. I think all of these test cases are good enough, honestly. Most of the time I have to write my own, though. So yeah, enough talking. Let's get to actually coding that out. So if it's null, we can purely just return null at this point because we're only checking one thing, which is easy enough. And this should pass that first test case. If I can, yeah, I think I can copy from here. And by that first test case, I mean the third test case. And it does. But moving on from there, we're going to have to actually flip some nodes. So if our root is null, we're going to just return the root. And otherwise, we're going to flip each of the children. So root.left and root.right. This is just a way in JavaScript to flip both of these without a temporary variable to swap each one of these. So root.right and then root.left. And we will return the root. And this should pass that next case as well. Or case 2, I mean, where we just flip one or one parent's children, to be clear. That's interesting. I thought they would have a... Oh, they do have a cool visual. So we expect for this one, we start out with 4, 2, 7. We flip the 4, or the 7 and the 2. The 7 is now on the left and the 2 is now on the right, but both of its children aren't flipped. So we need to just keep going. This problem is pretty easily broken up into smaller problems. So if we look at, I'll draw it out. I'm not sure how much it'll help though. So we have this node and this node. So its children, once we deal with this one and flip it, we can pretty much ignore these and pretend like we have more separate trees. Like these are now the root. And flip either one of these. So then we would just flip these and then move on, and then flip these to nulls because there's no children for these ones, and then flip these ones, and then once we run out of nodes to flip, we're done. Does anyone have any questions about the logic behind all that? Okay, so I just realized, as a side note, there's an arrow tool in here, and I've been drawing arrows manually over and over. So maybe I'll use them next time. Okay, so we need to iterate over these nodes somehow. And the first way that we're going to do it, and we're going to do it in 3 different ways just to get used to a few different ways of doing it with an easier problem. So since we already have this drawn out, I don't need to work through it again, or draw it out again. But we could either do it through depth first search or breadth first search. And for depth first search, which is the one people typically go for, I feel, because it can be done with recursion, is you start out with this node, the top node, and then go down further and further between each one. And then once you're done with all of these rightmost nodes, or it doesn't have to be the rightmost node, it could be the leftmost, but you go deep and then wide. So you're going this way, and then after that, go to this 3 node. And then after that, go over to this 7, then the 6, then the 9, etc. But for breadth first search, we would flip these top nodes first. So we would start at the top, flip both of these, and then flip the 2, or flip 2's children, and then flip 7's children. And then move on and flip all of the children's children. In this particular case, it doesn't really matter either way. But DFS is easier for JavaScript at least because there's no built-in queue data structure. We do have arrays, which will pretty easily allow us to make a stack, but queues are a different story. I'm not sure if we get anything. Nope, we get Lodash only, which I don't believe gives us any data structures. But please correct me if it does. I'll probably just go for doing an inefficient queue with an array as opposed to searching for a queue implementation when we get to it. So I'm going to start out doing iterative depth first search. So we're going to make a stack, which is going to be an array of tree nodes in our case. And at this point, our root, we know that it is a tree node because we already checked for null. And the first node we want to check in our stack is the root. So we're going to throw that in our stack. And then while there are still nodes to check, while the stack still has elements, so while its length is more than 0, we are going to do this logic. So instead of doing root left and root right, we want to reassign that, or probably not reassign, but declare a new variable to hold both of those to represent the current node. And to get that current node, we're just going to pop off the stack. And then this is going to give us it's giving us a TypeScript error because it's possibly undefined. But we know for a fact that since we're checking if the stack length is more than 0, there has to be an element in here. And that element is a tree node. So we can just tell it that this will never be undefined or null. To be fair, okay. I was going to say we could push null to it, but we can't because it's an array of tree nodes and not null. If we tried to push null to it, it would give us an error. Like if we did stack.push null, it says absolutely not. So after we flip these, we haven't really confirmed what these are at that point, or what the left and right nodes are. They could be null, they could be tree nodes, but the easiest thing to do here is let's just push to the stack if it's not null. So if root dot left is not null, then we're not going to return, sorry. We're going to do stack.push root.left. And then we're going to do the same thing for the right. Oh, we actually should not be doing root. I forgot about that. So these should all be current node. It does work, kinda. Normally, or I've had trouble with LeetCode where the Vim period operator does not actually repeat the action, but here it kinda worked. So let's try, oh well, I'm just going to ignore it. Yeah, that's annoying. I might just be doing something wrong though. So yeah, at this point, we just need to do the same with the right. And the reason why we don't want nulls in our tree node stack is because if we did have them, they don't actually have any children. They don't have a dot left or a dot right, so it would cause us some issues. Does anyone have any questions so far? Okay, so this should be everything we need. We're pushing to all of our nodes to the stack and then iterating over the stack every single time. So this should go over every single node. I've managed to not copy the last bracket every single time, I think. So if we test out all of these cases, it does work. And if we submit, it should work as well. And it does. Our memory is beating 5%, most likely because there isn't much memory to be saved with this problem. Yeah, let's see what this is 43 megabytes and this is 45. But yeah, there really is not much memory to be saved because you're not storing anything extra. We already have reference to all of these nodes. And it beats 42%. Last time I did it with the essentially same solution, just with gross formatting because I used Prettier. Yeah, that's the same exact solution. And it got much faster or much less memory. But yeah. So let's just run through what the solution is doing and then we can move over to doing some recursive DFS and then some, well, actually we'll probably go with iterative BFS first. DFS and BFS meaning depth first and breadth first search. Okay. Well, we can't really see this whole thing, but let's just assume that that looked less bad like this. Okay, so starting out on our stack, let's just make a tree that looks like this, or a simpler tree. We have 1, 2, 3, and then this one's gonna have 4 and 5. And I'm gonna copy that over here just so we know what it looked like before. This is the most beautiful drawing you've ever seen, I'm sure. Okay, so, and then here is a representation of our stack. So we start at this top node, and if it's null, which it's not, we're going to move on and add in our root to the stack. So now we have 1. And then after that, we're going to pop it from the stack and take both its children, 2 and 3, and we're going to flip them. Not sure if there's a good way to select anything here, but I'm just gonna flip these manually. So we flip it, so 3, and then 4, 5, and then 2 is here. And we add both of these to the stack because neither one is null. But first we're adding 2, or actually we're adding the left one, which used to be the right one. So we're adding 3 and then 2. Then afterwards, we pop 2 from the stack, flip its children. They're both null, so I don't need to draw anything out, but yeah. So then at this point, we don't push either one because both of its children are null. And we move on to the next iteration, where we have 3, which we will pop from the stack and then flip both of its children, which are 4 and 5. Then we get 5 and 4. And we push 5, then 4 to the stack because both of these are not null. And then for both of these, we'll flip both of their children. But since neither one of them actually has children, we're not going to push anything to the stack for either one. So I'm just going to skip this iteration since we've already been through that with 2. Anyone have any questions before we move on to the other ways to do it? Okay. So before I forget, we should go through time and space complexity. Since we aren't ever creating any new nodes, we're just holding references to them. We're not using any more memory, so it's O1 space. And then we go through each node once. So it's just O of n time, where n is the amount of nodes in the tree. And anyone have any question on the time and space complexity before we move on? Okay, so I'm just going to copy the solution real quick and throw it down here so we don't have to redo the solution or the DFS. So here is the BFS solution. Instead of our stack, we have a queue. I'm not going to do anything fancy for the queue, just use a regular array, which does have a worse time complexity, but just for the sake of time, I'm just going to say, let's assume that this is a queue with O of 1 enqueuing and dequeuing time as opposed to the current O of n in queuing and dequeuing time we have right now. So this is the same thing here. So we would do queue.shift, I believe. I'm going to check real quick. Well, actually, it will let me know in the other. So shift does remove it, and it returns the node. Okay. So we have shift, and instead of push, we're going to do unshift for both of these. And that's all it takes. So now instead of going through with depth first search, we're doing breadth first search. It's that simple. So if you decide to do it iteratively, you'll have a much easier time switching to a BFS if an interviewer by chance asks you to do it. So let's test this out, see if it actually runs and doesn't time out. I forgot the closing curly brace again. I'll do that every single time. So it does work. And we'll only ever have 100 tree nodes. So that didn't really change the time that much for this run. It's 2 milliseconds slower, but this tree is really not that big. And at any time with this version, I don't think we could have that many nodes in our tree. I'm kind of interested to see how many we might have though. So if we can have 100 nodes and we have, I'm gonna go on a tangent real quick though. So we have 1 and then 2 and then 4, 8, 16, 32. Adding those up, we have 7 plus 8, which is 15, and then 16 plus 32, 63, and we can't add 64 to that. So at most, we will ever only have 32 nodes in our queue. So it doesn't hurt us that much, but it would be much worse if it were a bigger binary tree. Yep. And just to get the I'll rename this one to 2 again to get the recursive approach out of the way. Instead of using a stack here and popping off the stack, I'm not sure. Oh, okay, because current node, we can just call it root. So let's just make a variable called current node, just so we can rename it. Call that root. We don't have stack here. We don't need to worry about these two cases because we catch them up top. So then at this point, we would just do invert tree, root.left, and invert tree, root.right. And I believe that should be it for this case. But I might be missing something since I did not test this out before. Let's try it out. And that works. Yep, it works. And it beats 99.29% of everything. So that's interesting. Yeah, the time is so much or so minimal that there's not really that big of a trade-off between, and just pushing to the arrays probably. Oh wait, this is the slower one, but still. Yeah, like the overhead of having an array and pushing to it and taking off of it probably takes up memory, and like even having extra variables, because there's quite a bit more variables going on here. Well, actually not that many more. But either way, we really don't get that much faster. We get 20 milliseconds on this run. And the difference in memory usage is, let's see, 44.4, 0.1 megabytes. So for this problem, it really does not matter. But typically, recursion uses more memory, just we don't recurse very deeply in this problem. Did I leave that in there? I think I deleted it. But getting down to 64, that's probably, I'm not entirely sure. So let's do 2 times 2 a bunch of times. 4, 8, 16, 32, and 64. That's only ever 6 deep. Not really sure how much those numbers matter. I'm just thinking, but here is how you do it recursively. You can see that the JavaScript takes a lot of the mental load off of you, I guess, because you don't need to worry about what's still here, but sometimes it can be a little bit harder to understand because we only run invert tree in here. You have to think about it a little bit longer. Not sure. But anyone have any questions since I'm just kind of talking? Okay, I don't think there's any questions. So maybe there's a question? Okay, no one has a question. Just someone commented to let me know that no one had questions, which I appreciate either way. Yeah, so that's that problem. I don't think I have anything else to say besides thinking about not important tiny optimizations between picking each of these methods. But yeah, this recursive way is still equivalent. It's still O of n time and O of 1 space. I believe it's still O of 1 space. I don't believe you count the extra calls in the, yeah. Not really sure how to say that, but yeah, I don't think it's counted. or the extra memory used to do recursion. I'll have to look up the terminology for that. I want to say in the stack, but I really don't know. But yeah, question 6 checked off the list. Next question will be valid anagram. I haven't looked at it in a little bit, but I believe you just get 2 strings and you need to check to see if they have all the same letters. Okay, I'm gonna stop recording and then let me know if you have any questions afterwards.